Today we must talk about a concept, state, and another concept, configuration. As I told you, in order to be precise, we must learn the meaning of words. The meaning of words is somehow arbitrary. It is a choice. So, somebody can use a word with one meaning, somebody can use a word with another meaning. I could talk hours about this. When I was more or less your age, I decided to start studying formal logics because I wanted to understand exactly what words mean. Okay? We will decide. In my opinion, if you start PhD studies, you must learn something about this. But now we use an informal approach, but we have to talk about the concept of state and the concept of configuration in more detail. Because we need a mathematical tool for describing the state of a physical system. And this mathematical tool is the space of configurations. Okay? So I am already framing for you the meaning, the different meaning of these two words. But we go ahead in giving more details about this. So, on this side of the blackboard, we represent phenomena and physical objects, or words talking about physical objects. So, for instance, we have the planet, one planet. Okay? One planet is a physical object. It is traveling around its sun. Okay? It is rotating around its own axis. It is subject to earthquakes. Okay? So you have many phenomena for this physical object. A state of a physical system, or a state of a physical object, is the picture in a given instant of what is happening to this physical object. A configuration is the mathematical model for a state of a given system. In order to understand this, we need an example. And I've chosen the planet. So, choose a reference frame and introduce the model material particle for this planet. So, you have, for every instant t, the position r of t of your planet. So you imagine that your planet is small enough that you can model it as a point. So let us understand this carefully. One planet, Earth, for instance, has a radius of the order of 1,000 kilometers. However, the Earth is traveling around the Sun with a trajectory whose dimensions are millions, 100 millions of kilometers. So you can neglect the small radius of the planet when you study the motion around the Sun. Okay? You have to be proud that Copernicus understood many of these things. Okay? So, the state of the system planet in the model material point is characterized by a vector, the position of the planet. So, three numbers, x, y, and zeta, or x1, x2, x3, three numbers are enough to describe the configuration of your system. Okay? Now you want to study for the same object, so for the same planet, you want to study another class of phenomena. For instance, you discover that sometimes you have spring, in another moment of the year you have summer, in another moment of the year you have winter. Here, in the mountains there, in winter time, you have snow. Not like in Warsaw, you have some snow on the top of the mountain. It's very seldom that you have the snow here. And now we are in a oven. So you must explain why this is happening. If you try to explain this with the model of material point, you don't manage. You need to introduce a more complicated mathematical model. The Earth is a sphere. You have a rotation of the axis solidal to the Earth with respect to the external axis. So, the same physical object, now you are modeling with a more sophisticated mathematical model. Instead of the position, now what you do? You take your planet as a sphere. You consider, for instance, its barycenter. Then you choose three axes of material points of this sphere. We carefully did all calculations, and we know that in order to know the orientation of these three axes, we need an orthogonal matrix. Remember, if you consider a placement of a body which is rigid, you can tell the position of all material particles of your rigid body if you know an orthogonal matrix. We did all the calculations. So, in order to follow the position of every material particle of this sphere, so if you have capital X, you want to know the position of capital X, you need to know the position of capital X naught, the bicenter, plus an orthogonal matrix Q applied to X minus X naught, where these are vectors, of course. Okay? This is something varying in time. This is something varying in time. When you block the material particle X, you get the trajectory of this material particle in time. So, if you know K of X0 and you know Q of T, you know the position of all material points of your sphere. Okay? So, the state of the system planet is now characterized in terms of a more complicated configuration. The more complicated configuration is given by a vector k of x naught and an orthogonal matrix Q. So now you start understanding something. The same physical object can be modeled with two different mathematical models. You can describe the behavior of the same physical object, a planet, introducing two different mathematical models. In this case, one mathematical model is richer than the other one. Why? Because in the first one, you are happy to know the position of one point of your point. Now, you not only want to know the position of one point, the barycenter, you want also to know the orientation of a solid frame of reference. Why you are inventing this more complicated model? Because if the sunshine is arriving in this direction, here it is hotter and here it is colder. If you want to model the fact that in 1 hour you have the sun and in another moment of the day you are in the dark, you need to say that this half is under the effect of radiation of the sun and the other side is in the shade. So, if your aim is to study the motion of a planet around the sun, this complicated modeling is not necessary. So the model of material particle is enough. If you want to know more, so if you want to model more carefully what is happening to your planet, then your mathematical model has to be richer. Okay? And you add some more mathematical objects, introducing a space of configurations which is richer. Okay, so the simpler model requires the introduction of a vector position. The richer model requires the introduction of a position plus an orientation. Okay? But you want to describe also earthquakes. If you want to describe earthquakes, you need to introduce a more sophisticated model, which we already discussed. If you have your planet, and if you introduce a function k giving you the shape of the planet in a given instant, then you are able to describe those movements of the Earth which are changing the shape of the planet. Okay? So what happens is that an earthquake is a deformation of the Earth. Of course, you cannot draw at this scale because they are movements of some centimeters, millimeters. But if you want to describe an earthquake, the model of a rigid body is not good. Or if you want to describe the movement of continental plaques, which are going one against the other for forming mountains, for instance, then you need even a more sophisticated model, because you need to say that the central part of the Earth is liquid. Then you need thermodynamics describing you the motion of heat from the center to the outside. Then you need to describe the deformation of the solid crust of the Earth. I could go on. I could introduce more and more sophisticated models. The physical object is always the same. The mathematical models you are introducing are more and more complex. Okay? Why I want to tell you this thing? Because usually people is confusing the mathematical model with the physical object. So for instance, if you talk about a planet, many persons think about the model of the material particle. This is deadly, because the physical object is something, and the mathematical model is something else. The mathematical model is to be chosen in order to describe the phenomena you are interested in. Because there is a bad news, a very bad news. There is no theory which is good for all phenomena. So when you decide to study something, a given class of phenomena, you must specify the class of phenomena you are interested in, and then you choose a mathematical model. This mathematical model must be complex enough to describe the phenomena you want to study, but not more complex. It has to be the simplest one which is able to describe the phenomena in which you are interested. Now I tell you an example, because we arrived at this knowledge after many discussions and after many efforts. Consider a physical object which every engineer should know, a beam. Okay? This beam could be the wing of an airplane. It could be the support of a roof. Something having the shape of a cylinder, the length of this cylinder being bigger, much bigger than the diameter of the section. Okay? Did you know that a French mathematician called Navier tried to study a beam deducing the equation of the motion for this beam, and in particular the equation for equilibrium of this beam, starting from the atom atomic structure of the beam? You know, in a delirium of omnipotence, these people believed that they could describe everything. They wanted a unique theory for every phenomenon. Okay? So Navier decided to introduce atoms, the interaction between atoms, every pair of atoms, and painfully started developing what is now called statistical mechanics in order to deduce the equations of a beam. Okay? You have to learn about this failure. Navier forgot some pieces in these equations while doing all these complicated calculations. And he forgot in particular shear deformation and shear stress in his equations. Using his Brown theory, he built a bridge. And while this bridge was being built, the pillar started collapsing. As he was a serious scientist, he didn't escape and he remained there measuring what was happening. What we have learned? We have learned that when your theory is too detailed, you know, do you mind about the destiny of one atom in a beam? Of course, if you are talking about a water molecule and you want to study the hydrogen and the oxygen energetic interactions, then you must know where an electron is. So if you want to understand the structure of water, you must follow the destiny of one subatomic particle. Okay? But if you want to study the deformation of a beam, who cares about the destiny of an atom? Nobody. We are happy to know what happens to an epsilon Cauchy cube whose side is 1 millimeter. Okay? Notwithstanding this, an engineer needs to know at least 3 theories when he wants to describe a beam. He needs to be able to treat the beam as a rigid body. He may need to describe it as an Euler beam, or he could need to describe it as a first gradient continuum. 3D. In engineering practice, practically speaking, in everyday life, in some conditions, you can model a beam as a rigid body. In another situation, you can model it as an Euler beam. And in another situation, you may need to describe it as a 3-dimensional continuum. For instance, your worker takes this beam and is transporting it to mount it, or your lifting system needs to pull it up to place at the top of the roof. Do you need to study the deformation of this beam? This is not necessary. So you can model it as a rigid body. When you have a very long beam, loaded in particular ways. So, for instance, you have a beam and you have a uniform load applied at the top of it. Then, Euler beam theory is very good. But imagine that you are a bad boy. You take a beam like this. You apply here a very concentrated and high force, and you apply here a very concentrated and high force. Which will be the shape of this beam? This one. Can you apply a model in which every section remains rigid? Of course you can. Then you are obliged to introduce a one first gradient three-dimensional continuum model. Do you believe that this is theory? That this is philosophy of crazy people who spend their time wasting intellectual energy for doing useless things? Now, I tell you a story. Close to the residence where you are sleeping, they built a sport palace. If you manage to take a glance inside, you will see that the roof is made of wood. Wooden beams. Okay? The engineer who was designing that roof came to us with a stupid calculation made using the theory of Euler beam. Okay? The old engineer who was checking the calculation of the young one was very worried. You have a beam which is long 57 meters, and you have a piece of metal of 10 centimeters blocking the extremities of this beam. The engineer, the old one, was very worried. So they called us. Okay? And I started examining as a student, as if he were a student, the engineer who had designed this beam. So I asked him, which is the model you are using? He said, I don't know what you mean with model. I said, okay, which is the software you are using? He told me SAP, S-A-P. I knew that SAP is using Euler beam model. Okay? Why this is very stupid? Do you know how a composite multi-layer wood beam is made? You take a section and you have one layer of wood, one layer of glue, one layer of wood, one layer of glue. You press these together, and at the end you get something which resembles a beam. Okay? But who can believe that this section is rigid? I mean, this, if you ask your grandmother and you tell her, I have a beam made of metal, and I have a beam obtained gluing together some narrow layers of wood together with glue. even if she is not an engineer. Your grandmother will tell, what are you doing? Okay? So, I asked Ivan to do a numerical simulation using Nastran and a 3D model. So, we introduced one layer of wood, one layer of glue, so we reproduce exactly the reality, and we loaded this beam following the standard loads we were expecting, and we discovered that close to the pivot at the extremity of the beam, we had shear forces, so forces which were detaching the glue, okay, 7 times bigger than the maximum amount of shear that glue could sustain. I said this to the engineer, and he told me, you are a mathematician. You know, these years, to be a mathematician, it is not like in the year of Copernicus. The years of Copernicus, to be a mathematician was very good. Mathematicians were very well considered. Now, if somebody tells you that you are a mathematician, you know, it's more or less, it is better to be raping children. If you rape children, you are better than a mathematician. Okay? It is a terrible insult. I said, okay, do what you do. We expected some time, then in Udine, in the province of Udine, the same roof was mounted. It collapsed while they were mounting it. The consideration about the mathematicians increased here, and now they have built that roof in this way. They added some metallic bars at the extremities, and they screwed these metallic bars very tightly in order to reinforce the final part of the beams. And the collar, it is not anymore 10 centimeters, it is 40 centimeters. Now, why I'm telling you the story? Because I want to prove you that the philosophical discussion we are doing about different models for the same physical system, the choice how one has to choose the correct model for describing the right phenomenon, this is not only something which has to be understood by a researcher, a PhD student, a professor teaching at the university. This must be part of the knowledge of a practical engineer. And it was part of the knowledge of a practical engineer. Because the old engineer in this story, he was frightened. The young one, he told me, I use the computer. The computer tells me that it works. Okay? So, you must be very careful. Okay. Now, I use the word state talking about physical objects. When I use the word configuration, I'm talking about a mathematical object. The set of elements of a configuration space is the set of mathematical objects which I use in my given model to describe the state of a system. So, let us give some examples. R3 is the set of 3 real numbers. This is the configuration space of the planet when I use the model material particle for describing the state of a planet. R3 Cartesian ort. So 3 numbers plus an orthogonal matrix. So the set of all triples plus all orthogonal matrices, triples of real numbers and orthogonal matrices. This set is the configuration space of a rigid body. The set of all C2 functions defined in a reference configurations and having values in the Euclidean space of positions. We met this people, the function placement chi, which we have already made. This is the configuration space of a deformable body. So the same physical object can be modeled either with this configuration space, or with this configuration space, or with this configuration space, depending on how detailed you want to describe the phenomena you are having in your hands. Okay? Clear? I am afraid that all these things you will not find written very often in the books. Okay? These things were taught to me by Ettore Mancini. He was an experimental physicist. Okay? But he had a deep theoretical knowledge. Okay. Now we have to discuss about the structure of configuration spaces. So we have to talk about degrees of freedom. Now, this concept is not talking about a physical system. You cannot tell that the Earth has 6 degrees of freedom. Because the concept of degrees of freedom is relative to the space of configurations. So I can tell you the story. When I was waiting my turn to pass the exam of rational mechanics, I have seen this event. Somebody sitting, the professor asking him, now talk me about the concept of degrees of freedom. He said, the Earth has 6 degrees of freedom. Without telling anything, the professor said, okay, you failed. Next one. Because it is like talking with the wrong conjugation of verbs, or using accusative instead of using nominative. Your language is using the gradations, right? So you know that accusative is different from nominative. If you use nominative instead of accusative, you cannot speak your language. So you don't need to go ahead. You must come another time. learn better your language and then you know. Okay? The syntax of mathematical modeling requires that when talking about degrees of freedom, you are not talking about the physical object. You are talking about the space of configuration. So you are talking about the mathematical model you are introducing. How many real parameters do you have in R3? You have x1, x2, x3. So, in order to characterize the configuration of an object for which you have chosen the model material particle, you need 3 real parameters. Therefore, the degrees of freedom of the model material particle are 3. Okay? Now, you need to spend a little bit more time to understand how many degrees of freedom you have for a rigid body. Okay, I give this to you. You must start learning to go and read in books some. In the books I gave you, these things are written, but you must find them by yourself. This is a part of learning process. Okay? Now, I tell you that the degrees of freedom of a rigid body are 6. 3 parameters you need for R3, this we have already learned. For characterizing an orthogonal matrix, you need 3 angles, which are many, can be different angles, but we can use Euler angles. Okay? So, write down, find Euler angles, and understand how an orthogonal matrix can be characterized in terms of Euler angles. Okay? Now, I must tell you a story. When I believed that I was professor at the University of Rome, because now I'm not anymore professor of anything, because every student must pass the exam. The director sent me a letter and said, everybody must pass the exam. So I'm not examining anybody anymore, because I'm a serious person. I passed them, period. Okay? When I was a professor, I asked to a girl student, how many degrees of freedom you have in the model of a rigid body? I never understood why she answered 9. This is something which I never understood. I tried to understand which was the reasoning in her mind. The number of degrees of freedom in a given mathematical model is the number of real parameters which you need to specify every element in the space of configuration. Okay? In rigid body theory, you need 3 numbers for the position of the barycenter and 3 angles for each orthogonal matrix. Okay? So the degrees of freedom are 6. Now, which are the degrees of freedom of the model? The form of body, my dear friends, your this story has been understood very well by Banner. And it is rather complicated. Okay? So what we know, what we will do now, we will understand that this number of degrees of freedom is infinite. So we will stop at a very superficial layer. Okay? However, you must understand the big difference between the first two models and the third one. Because a computer can do only a finite number of calculations. So a pool computer can manipulate only models in which you have a finite number of degrees of freedom. So we will need to work a lot to take a mathematical model with infinite degrees of freedom and reduce it to a finite dimensional model. So when you are writing equations, then you are introducing finite elements. What are you doing? You are taking a complex space of configurations and you are reducing it to a single space of configuration. In particular, what you are doing? You are taking an infinite dimensional space of configuration and you are forgetting about some of the degrees of freedom and limiting yourself to a finite number of degrees of freedom. Okay? So now we start talking slowly about this concept. And we go back to functions and to Weierstrass theorem we have already discussed. So you consider an interval AB and you consider the set of all functions defined in the interval AB. Okay? Now, we start considering polynomials. So, let us consider the set of all polynomials having a degree smaller than n. So, this is the set of functions which you can build in this way. Okay? So, let us discuss a little bit this space. If you sum two polynomials of degree n, you get another polynomial of degree n. You agree with this? Okay, so P1 belongs to Pn, P2 belongs to Pn, implies P1 plus P2 belongs to Pn. Okay? Don't be afraid. This formalism is opening your mind. You must use mathematical formalism. If you multiply a polynomial times a real number, you get another polynomial. Okay? given the polynomial with a0 equals 0, a1 equals 0, an equals 0. We call it the zero polynomial. P1 plus 0 equal P1. Forever is P1. If you consider minus a0 minus a1x minus anx to the n, and you call this minus p plus minus p equal 0. Do you have understood that the set of polynomials of degree smaller or equal to n is a vector space? It has exactly the same structure as the set of arrows we use for displacement. So we can talk about a basis of Pn. A basis of Pn is a set of polynomials such that you can write all other polynomials in terms of linear combinations. So, do you remember what is a basis in a vector space? A basis in a vector space is a set of independent vectors which verify the following condition. Every vector can be represented as a linear combination of your given vector base. Okay? Now, consider this set of polynomials. The polynomial which to x is associating 1. This is a polynomial. The polynomial which to x associates x. The polynomial which to x associates x to the power n. So I can call this E1, E2, E3. Equal double dot means that you know the meaning of what is left here, and in this way you are giving a definition for what is right. Okay? This is a very precise way of talking. Okay? Now, for every P equal sum I from 1, why is it in 3? Yeah. From 1 to, okay, maybe we have to call this 0, this 1, so we keep the power, because this is x to the 0. Okay? For being precise, we do this way. Okay? So, sum from I from 0 to n of a n, a I, e I. I leave you the following exercise. Prove that E0, E1, En is a set of independent vectors. Okay? If you know this, and as this equality is trivial, okay, because every polynomial is a0 times 1, a1 times x, an times x to the n, so this equality is trivial, okay. What we have proven, every polynomial of degree n can be uniquely characterized in terms of n plus 1 parameters, a0, a1, an. So, how many real parameters do you need for specifying in a unique way a polynomial? You need n plus 1 parameters. So, if you use the set of polynomials as a configurational space, a space of configuration, then this space of configuration has n plus 1 degrees of freedom. Now, when you talk with engineers, they are very proud. My software uses 1 million of degrees of freedom. Okay? He's talking about this n. He's telling you that he is considering many polynomials, okay? And the sum of all these n's is 1 million, 10 millions, okay? Okay, but even if you have millions of millions, many millions, okay? If you have a poor continuous function, to go close to this poor continuous function, you need a polynomial whose degree is high. Very high. To approximate every function, every continuous function with Weierstrass-Dirichlet, you need polynomials of degree as high as every natural number. So the bad news is that you need infinite real parameters to approximate every continuous function. So the set of continuous functions has an infinite dimension. This is very difficult to understand. But if somebody explained you when you were a child that square root of 2 needs infinite digits, and if you stop with finite digits, you get an approximation of it, but you never get exactly square root of 2. You are ready to understand this. Now, I try to explain you this carefully. Polynomials are like rational numbers. Continuous functions are like real numbers. Where every real number is the limit of a sequence of rational numbers. Every continuous function is the limit of a sequence of polynomials. Every rational number can be represented as the ratio of a natural number p divided a rational number q. So you need a finite number of symbols for representing a rational number. So a rational number is computable. Okay? A polynomial is characterized by a finite number of real numbers. So you can characterize a polynomial with a finite number of numbers. If to each of these numbers you replace a rational number, a polynomial is computable. So you have a problem to find the shape of a beam. You have some equations, you have to solve these equations for forecasting what happens to your beam when you load it. How you are working? You choose a polynomial which is close enough to your solution for giving you the correct approximation in your particular situation. Okay?